This is part 2 of Cosmology and Astronomy. We're going to start with the Wien's Displacement Law. Then we will move towards Stephan-Boltzmann Law, and then we're going to understand how to use both of them to find out the radius of a star. Okay, so first, this is based on common observation, by the way, the Wien's Displacement Law, that lambda and temperature are connected or are associated with each other. But how are they associated? This is what is important. So what is Wien suggesting? So Wien says that lambda, or the wavelength that is observed, that you see with your own eyes, is inversely proportional to the temperature of the surface of that planet. So if you observe a larger wavelength, for example, if you're observing a red color, then the temperature of that planet will be less. And if you're observing a smaller wavelength, let's say closer to blue light or violet, which is approximately 400 nanometers, then your temperature of that surface, the surface temperature of that planet or that star is going to be greater or higher. This is why this is a common misconception that the red star appears to be hot, but no. Red stars, since their wavelength is larger, their temperature is less. They are supposedly, or you can say they are cooler than blue stars, which have a temperature of 10,000 Kelvin. So just by looking at the color emitted by a star, we can predict its temperature. Of course, it comes with its estimations and problems, but on the grand scale, this is an acceptable equation. So if you convert this equation into an equality, this looks like this: lambda multiplied by temperature is equal to a constant k. The value of the constant is given at this point. Okay, now let's try to understand. Look at the table over here that's on the right side. So the stars giving off blue color have a temperature in the range of 33,000 Kelvin, and the stars in the range of red color have a temperature of 3,700 Kelvin. Our star, the sun, appears to be in this category, yellow-white or yellowish color. And fair enough, the temperature of the surface of the star of our sun is 5,800 Kelvin. We'll do a question regarding this topic as well. Now, what does Wien's displacement law also tell us? What are these graphs? What is this representing? So point number one, the shorter wavelength or smaller wavelength at the peak intensity is higher temperature, right? If the temperature of that body is higher, then the wavelength appearing at the temperature will be smaller. And this is what we understand at this point as well. If the temperature is greater, then the wavelength appearing at the maximum brightness or intensity will be lower, right? And let's get to this point. We'll get to the example of the sun in a moment, okay? Let's try to understand this graph. You see, higher temperature, 5,000 Kelvin, the intensity graph appears to be at a higher level as compared to 4,000. You see, what is the meaning of this first point? You see, even at 580 wavelength, let's compare this. At 580, this 4,000 Kelvin temperature star is representing this intensity. And the 5,000 Kelvin star is representing this intensity, even for the same wavelength. This is what is the meaning of the first point, right? That greater wavelength will be representing the temperature. Now, what is the meaning of this peak value? Basically, this Wien's displacement law is not the wavelength, not any wavelength. It is the wavelength of the maximum brightness or the maximum intensity. What do you see with your eyes in terms of maximum brightness? What does the star appear to be? Now notice for this blue star, for example, it's not possible. It's not like this, that it's only emitting blue radiation. It's also emitting all the other spectrums as well. But out of all the other spectrums, the one that has the highest intensity is blue. Even for our sun, it's emitting all radiation. It is emitting infrared, it is emitting ultraviolet, it is also emitting the visible spectrum as well. But why do we see our own sun to have a yellow or yellowish orange shade? Because the wavelength it is emitting at that point belongs to yellow color, and at that point, that is the maximum brightness of that wavelength. That is exactly at this point. So we can predict the temperature using the Wien's displacement law. And for all the other stars, the brightness that you will see, the color that you will see, will help you predict. Now, for example, for this blue star, the highest intensity wavelength, let's say at this point, will be of, let's say, the blue color, which is 400 nanometers. For this yellow star, the graph is going to go something like this. And at the highest intensity at this point, The highest intensity will be somewhere around the color of yellow, which is 500 approximately, or orange, which is 550. And for this red star, if we were to look at the graph, this is going to be approximately like this. And the highest intensity will be around 700 nanometers. So this Wien's displacement law actually tells you that the highest wavelength observed with human eye, of course, we are going to replace human's eye with detectors, but the highest intensity observed will correlate to the temperature of that or the surface temperature of that planet. Okay, and it does not mean that the rest of the wavelengths are not available. They are also available. Notice that if I look at this graph, let's say this wavelength is also available, this is also available, this is also available, but the largest, or the wavelength corresponding to the highest intensity will give me the information about its surface temperature. This is Wien's displacement law. The second point to this is that the greater intensity of electromagnetic radiation at each wavelength. Notice that at 5000 and at 4000, we can compare the relative brightness or intensity of the same wavelengths as well. You see, at 725, at 4000, this is the intensity. For the same 725, the star that has a higher surface temperature, the intensity is also greater for the same wavelength. Now, this is the idea. This is the relationship of Wien's displacement law, which helps us to predict the surface temperature based on the wavelength data. Okay. Now, let's move on to this example. Now, this is a daily life example. Is Wien's displacement law only applicable to astronomical objects? No, it is also applicable to real life objects around us. If you increase the temperature of any metal, you can see that as it approaches higher temperature, its wavelength starts to change, right? And wavelength decreases. First, it starts with an orange tint, then goes to white hot, and then eventually a blue flame or a very bright white flame will have a very high temperature. That's why the blue flame that we have in our houses on stoves has a higher temperature than a red flame gas or red flame stove, or if we are using gas that produces red flame, its temperature will be lower than the blue flame. Anyways, moving on to the example of our sun. How do we apply the Wien's displacement law for our sun? You see, this graph is again an approximation for our sun. The highest intensity we can see is at a radiation of approximately 500 nanometers. Can we use this data to predict the temperature of the sun? So let's use Wien's displacement law, which is lambda max. Again, why do we call this lambda max? The wavelength at which the intensity is maximum. We can see that the rest of the intensities or the rest of the wavelengths are also available from the sun, but we're only interested in that wavelength which is the brightest, which has the highest intensity. So this is going to be equal to a constant, right? We have the wavelength, which is, let's say, 550 nanometers for the sun, approximately 500 nanometers for the sun. We don't know the temperature, and the constant is 2.9 into 10 raised to the power minus 3, which is written over here. You don't need to convert this minus 3 into anything, but this is going to be converted into minus 9 of nano. So this is going to be 2.9 into 10 raised to the power minus 3 divided by 500 into 10 raised to the power minus 9. The temperature comes out as 5800 Kelvin. If you go online, you will realize that this is the temperature of the surface of the sun. So this equation helps us to predict the surface temperature based on observation. This is what we see in the laboratory. This is the color that we see in the lab. It will help us to predict the surface temperature of that planet or of that star, for example. Moving on to Stephan-Boltzmann law. Now, Stephan-Boltzmann law will help us to figure out the radius of that star. This is why this equation exists. We find temperature using Wien's displacement law. We find radius of the star using Stephan-Boltzmann law. There is going to be a procedure for that. Now, in order for us to use this equation, there are going to be some assumptions. The luminosity of the star depends on two factors. The thermodynamic temperature, how brightly it is glowing, how much power it is developing, is going to be dependent on the temperature and its radius. Temperature will be found by lambda max T equals to constant, the Wien's displacement law, and radius will be found by the Stephan-Boltzmann law, which is this equation, L equals to 4 pi sigma r squared T raised to power 4. The value of sigma, or the constant, is this, and of course it has been found by experimentation. It's a universal constant, just like gravitational constant. And you can pause the video and read these points, but I've explained them already. The main purpose of Stephan-Boltzmann law is to find out the radius of the star. And there is going to be a step-by-step procedure for that. Let's apply those step-by-step procedures that I've discussed earlier, that first we find temperature, then we find the radius, in this example that is given to you right now over here. He says the temperature of the sun is 5800, the peak brightness is 500, the peak brightness for another star is 120. Find out the radius for this. Now first we will use the Wien's displacement law to figure out that for this star, Sirius B, what is the maximum wavelength, what is the maximum temperature of the star? So lambda max into T equals to a constant for our own sun, which will be constant, which will be equal to lambda max into T for another star. So this is going to be something like this. So this data is for our own sun, and this data is for Sirius B that is given in the question. So how, although we could have done it by putting the constant in this, but since both equations, both parts are equal, let's do it directly. So this is going to be lambda max, which is 500 into 10 raised to power minus 9. Temperature is 5800 equals to the lambda max of the other planet is 120. So this will be 120 into 10 raised to power minus 9 into the temperature. Now, when you find out the temperature of this star, this is going to come out as 24,166 Kelvin, which is rounded off to 24,200 Kelvin for the sake of simplicity, right? Now, again, our first step was to find out the temperature, which we have done using Wien's displacement law. The second step will be to find the radius using Stephan-Boltzmann law, which is this equation. Now, let's apply this equation. So he says, for the second part, that the brightness, or you can say that the luminosity of the star is 0.056 times of the sun. Do we have the value for the sun? Yes, we have the value for the luminosity of the sun, 3.83 power 26. So L equals to 4 pi sigma r squared t raised to power 4. L will be 3.83 into 10 raised to power 26, but multiplied by 0.056 because it is not as bright or not as powerful as the sun, equal to 4 pi sigma is 5. Let me go back to the standard value, which is 5.67 minus 8. 5.67 into 10 raised to power minus 8. R square, radius square. Do we know this? We don't know this. Again, it is being multiplied, so I'm just writing this over here because I don't have enough space. And the temperature was found from the previous part, which is 24,200 Kelvin. But please be advised, this has a raised to power 4. Make sure that you take care of the values. Now, at the end, R is going to be squared. So whatever answer you have, please don't forget to take the under root. Your R is going to come out as 9.36 into 10 raised to power 6 meters, which means that the radius of the star is this much, and its luminosity at the surface is 0.056 times of the sun. So that is how we use the Stephan-Boltzmann law to find out the distance, the radius of the star. So ideally, we have completed the whole topic as it is, but let's go to the questions asked by the examiner in the past papers. This question is question number 9, part C, May 2023, paper 4.2. He tells you that this is the radius, this is the luminosity. He wants you to find out the surface temperature of this star. So pause the video, try this on your own, see if you can do this. Okay. So we have the Stephan-Boltzmann law equation, which is L is equal to 4 pi sigma r squared T4, right? So let's replace the values. Let's see, this is the radius r, this is the luminosity L, and we want to find the temperature. So L is going to be 1.4 into 10 raised to power 28 equals to 4 pi. Sigma is 5.67 into 10 raised to power minus 8. This is given in the data booklet. The radius is 2.3 into 10 raised to power 9 being squared t raised to power 4. Please make sure this is power 4. Don't forget to take this root over there. This is going to come out as 7806 Kelvin, but up to two significant figures. This will be 7800 Kelvin, right? Question number 3. In question number 3, since we are dealing with part C, in a previous part, they have already calculated, or you can say they will ask you to calculate the temperature, which is 6980. We're going to use this value in the incoming part. That's why I'm just picking the value over here directly. So this is question number 3, October-November 2023, paper 4.1, part C1. He says that the star in B, of course, the value picked from that part, has the radiant flux intensity to be this one, okay? And the formula for radiant flux intensity was F equals to L divided by 4 pi d square. when observed at a distance of this, so this is this value is given to us. Okay. Calculate the luminosity of the star. Let's try to do that. So we have a very straightforward formula, which was F equals to L divided by 4 pi d square. F is given to us as 2.52 into 10 raised to power minus 8 equals to L is what we want to find out, divided by 4 pi. D is also given 4.16 into 10 raised to power 16. Don't forget to take the square. Then L comes out as 5.48 into 10 raised to power 26 watts. So this is going to be 5.48 into 10 raised to power 26. Unit is going to be watts. Then he asks you to find out the radius of the star again. This can only be done by using Stephan-Boltzmann law, which is L equals to 4 pi sigma r squared t raised to power 4. L is found in the previous part, which is 4.48 power 26. 4 pi sigma is 5.67 into 10 raised to power minus 8. R square is what we want to find out. So R square is going to stay as it is. Temperature raised to power 4 is what we needed from the previous part, 6980 raised to power 4. So 6980 raised to power 4. Please don't forget that this is a square. This will be taken as under root on the other side. So R comes out as 5.69 into 10 raised to power 8 meters. So the radius of this star is this value. Okay, all right. Moving on to the next part, which is October-November 23, question number 10, paper 4.2. He says, identify Wien's displacement law. You just have to write this down in English. You will simply say that the temperature of the surface is inversely proportional to the maximum intensity, or you can say the maximum emission rate wavelength, or the wavelength of the maximum emission rate. You can just memorize the answer of the marking scheme. I've explained it, how this Wien's displacement law actually works. Okay, so he says that a cosmology student observed the electromagnetic radiation of the star galaxy. Student uses Wien's displacement law. Now, this is very important. He is mentioning what formulas are being used to find what? The surface temperature. So coming back to this table, okay, so the wavelength and the surface temperature are connected or found by Wien's displacement law. So we need to write this down as lambda being equal to 1 over t. Okay, all right, for both of them. Then he says that the uses to measure the surface temperature. Okay, fine. A standard candle is used to measure the distance. So if a standard candle is being used to measure the distance of the star or the galaxy, the formula for that comes out as F equals to L divided by 4 pi d square, right? Okay. The third part, he says that the Stephan-Boltzmann law is used to estimate the radius. So the third part says radius of the star is being found by the Stephan-Boltzmann law, which is L equals to 4 pi sigma r square T4. All right. So these are the formulas that will be used to find out what are we going to figure out for this table. Okay. So, but first let's get to this table. It says student observed the radiation and the star is red shifted. So what is meant by a standard candle? So an object or an astronomical object of known luminosity, and we have understood this in part 1 as well. State the reason why radiation from the star is red shifted, because galaxies are moving away from each other. I'm not talking about this redshift and the Big Bang Theory and the expansion of the universe, because that is going to be in part 3. So I'm just writing these answers down. Okay, now this is where things get a bit tricky. He says the true values of the galaxies observed are just estimates, or estimated are those that are corrected to allow for redshift. There is a formula for redshift that is going to be in the third part of the video, which is delta F divided by F equals to delta lambda divided by lambda, approximately equal to V divided by C. Okay, and we observe in this redshift that all the wavelengths are generally increasing. So the wavelengths increase because of the redshift, right? So what happens now? He says by placing the tick in each row, complete to indicate that how the observations and estimates may the student compare with the true values. He says that he is not correcting the values. He is not compensating for the redshift. What effect would it have on the true answers if the redshift is not involved? Of course, he's going to get wrong answers, but how wrong these answers will be. Are they going to stay the same, or will they be too low, or will they be producing too high an estimate? So first we need to understand that because of the redshift, the lambda is going to increase. Okay, so lambda, the wavelength will be too high because of the redshift, right? If because of the redshift, the wavelength is too high or estimated to be too high, then the temperature will be too low, or the temperature is going to be lower than expected. So that's why we are choosing too low. Then distance to the star. Now in this equation, the standard candle luminosity is already known. The flux intensity or the luminous intensity is already known. So the distance to the star will be the same. It will not be affected by these things because there is no wavelength dependence. There is no temperature dependence in this equation, mathematically speaking. Moving on to this last part, he says the radius of the star. Now this requires a bit of, you can say, a bit of an understanding. So the radius of the star, let's make R the subject of the formula. This is going to be L divided by 4 pi sigma t raised to power 4 being proportional to or equal to r square. Now, since L is a constant, because this is what we developed our previous answer based on, right? So if L is a constant, 4 pi is a constant, sigma is a constant, what are we left with? Temperature being inversely proportional to r square. So r square being proportional to, inversely proportional to T4. What happened to T4? T4 was too low. If this is too low, then R is going to increase because it is an inverse relation. So this will be too high, right? So these are our final answers. How we tick these answers, what's the logic behind them? This is how we've done that. And of course, we need to understand that how did we get to these formulas? Because he has mentioned everything in this paragraph. Which formula is being used for what? But the starting point is going to be the redshift. That wavelength is going to be too high because of the Doppler effect on redshift. And I will be covering that in part 3.